This video is looking at some triple content from the topic B5, homeostasis and response, and we're looking at the eye. So if we look at parts of the eye, the outer edge of the eye is called the sclera. Okay, so it's really tough. If you've seen dissection of an eye, you'll know it's really difficult to get into. Very strong outer membrane of the eye. We've got the cornea, which is where light is refracted through as it goes into the eye, and the cornea can be reshaped in laser eye surgery. It can have a contact lens sat on top of it to change the shape of it, to refract the light in a different way so that it forms the image at the retina at the back there. We've got the pupil, which can dilate to allow more light through, so that means get bigger. It can also restrict the light. When it's a really bright day, the pupil is much smaller. Okay, and you get that pain when you turn the lights on in the morning, because when it's dark, the pupil's really wide, allowing lots of light through, and as soon as you turn the lights on, the pupil's got to adjust to that, and at that point in time lots of light is going into your eye and it's actually hurting the back of your retina, so that's why we get that pain when we turn the lights on. We've got the lens, which is able to change shape again for changing the refraction of light, and this is to focus on close and distant objects. The iris has two lots of muscles, the circular muscles and the radial muscles, and we'll look at how they adapt to change the size of the pupil. The iris is the coloured part of your eye, and that is controlling how big the pupil is. And then we've got the ciliary muscles and the suspensory ligaments, and we'll look at those in more detail shortly, which help to control that width of the lens. We've got the retina at the back of the eye where the image is formed, and then we've got the optic nerve, which is taking all the information to the brain. So we've got a bit more detail here. You can see the top picture there is showing you all of the different muscles that hold the eye in position. We've got the sclera, which I said was the tough supporting wall on the outside of the eye, the cornea where light refracts going into the eye, the pupil where light enters the eye, the lens that focuses on our near and far objects or surroundings, the iris, which controls how much light goes into the eye using the radial and circular muscles. We've got the ciliary muscles and suspensory ligaments, and they muscles, remember, can only contract and relax. Okay, so they help us to change the shape of that lens so it changes the amount of refraction and therefore focusing on those near and distant objects. The retina, where the image forms, it actually forms upside down. On that point, we need all of the focal distance to be the length so that it hits that retina, and we'll talk about that with some pictures shortly. But we need the focal point to be on the retina in order to see accurately. And then the information from the retina is taken to the through the optic nerve to the brain for processing to turn that image up the right way. So focusing on a near object, okay, so we can see here that the lens is really quite wide, and to make it wide, the muscles, the ciliary muscles, have contracted and the suspensory ligaments have loosened. If you think they need to loosen to allow it to kind of get fatter and shorter and wider, okay, so the lens is thicker, it's going to refract light more to look at a close object. Now, how are we going to remember this? If the object is close, that begins with a C, the ciliary muscles contract. Okay, we've got all of our C's here, so close, ciliary, contract. Okay, so hopefully that's going to help you with how we see close objects, because the ciliary muscles are contracting, the suspensory ligaments loosen, and that's because it's gone kind of fatter, more like a C shape really, isn't it? The actual lens has become more curved like a C shape, so hopefully that's going to help you. Thicker lens refracts the light more strongly, okay? So that's how we see the close objects. Looking at distant objects, then, you can see there's a noticeable difference in the shape of that lens. It's much, much thinner, and we've got the opposite happening of what we had on our close objects. So here the ciliary muscles are now relaxed, the suspensory ligaments are pulled tight. So if they're pulling tight, they're shorter, which is really stretching out that lens, making it much thinner so that it doesn't refract the light as much. And that's viewing our distant objects. Okay, so let's just go back and do a quick review because there's a lot going on here. We've got close objects, ciliary muscles contract. We've got all the C's, and it causes the lens to look more like a C shape. It's much fatter and wider, refracting more light, and the suspensory ligaments have loosened to allow that lens to almost get a bit shorter where it's got a bit wider. And then for the distant objects, that lens has got much thinner, a bit taller because it's being pulled out, stretched out as the suspensory ligaments are pulled tight, and the ciliary muscles have relaxed to allow this to happen. Okay, because as they've relaxed, it's allowed those suspensory ligaments to pull tight. This is refracting less light. The light at less of an angle of refraction because it's thinner. Okay. Now, in the course content, actually talks just about how dim light, how the eye adapts for dim light. But we're going to look at bright light, and actually dim light is just the opposite. And we've got a bit of alliteration here to help us. So in bright light, we're bright-eyed, we're ready for everything, we're alert. That's where we get our alliteration. So radial muscles relax, circular muscles contract. So R and R, C and C. Okay, that allows the pupil to let less light in. So when we're bright and ready for action, radial relax, circular contract. In dim light, we're kind of stumbling around, we've lost our way because it's dim, it's dark, so we lose our alliteration and we get opposites. Okay, so the radial muscles contract, circular muscles relax. That dilates the pupil and lets more light in. Okay, so think about it as you're confused because it's dim light, you don't know where you're going, you lose all of your alliteration. Radial muscles contract, circular muscles relax. Now we need to look at short-sighted and long-sighted. Some of the pictures you see of this, they will just show a circular eyeball, and it will just show a difference in the focal length. We can actually see here that short-sighted, the eyeballs almost become a bit squashed, a bit longer, and in long-sighted it's actually become like a bit squashed in the other way, so it's become a bit narrower and a bit taller. Let's have a look at how we correct this. So this is our short-sighted. If you're short-sighted, you can see things at close range. And if you're short-sighted, you have a short focal length. So you can see that where those rays of light have crossed over, they're not meeting the retina. They're kind of in the middle of the eyeball there. It's a much shorter focal length or focal distance. So short-sighted, you can see things up close and there's a short focal length. So what we're looking for is to extend that focal length, and we can do this using a concave lens. It's actually really a biconcave lens because it's concave on both sides. And this is going to sound silly, but basically concave goes in, and if I was in a cave, then I would be able to see everything that's close to me because everything would be a short distance. So short-sighted, everything's close. I can see everything because I can see everything that's close by. And I use a concave lens. It's just a silly thing that hopefully will help you remember that concave goes with short-sighted. So what the concave lens does is it kind of widens out the beams of light. So it's kind of refracted them out. And that means that it's allowed a greater distance in the focal length to bring those back to a point at the focal point, and it's hitting the retina. So on the right hand side there, you can see the focal point hitting the retina, which is where it needs to be in order to focus that image correctly. So short-sighted, short focal length. If we're short-sighted and we're in a cave, we can see everything. In a cave means we're going to use the concave lens. And it's pulling out that focal length, increasing the focal length so that it focuses on the back of the retina there. Let's have a look at long-sighted. So long-sighted, long focal length. You can see the focal point is actually beyond the back of the eye. It's gone beyond the retina. So we need to try and pull that in a bit before so it can shorten that focal length, and we do that with a convex lens. Okay, so the opposite of concave is a convex lens. And what that's doing is, you can see it's shortening the focal length, allowing that focal point on the back of the retina again, just like it did in the reverse in the previous one. So bringing that image so the focal point is on the back of the retina. Final part of this video is looking at correcting defects. Okay, spectacles, they call them spectacles in the course content, not glasses, but I'm sure you can call them glasses. That's what we've just been looking at, the concave and the convex lenses. Hard and soft contact lenses, so this is our permanent and temporary kind of everyday, once a day use contact lenses, and what they're doing is they've got a slightly different thickness at different points, it sits on the cornea and it changes the refraction of light through the cornea. We can have laser surgery, which does a permanent change of the shape of the cornea, so there's no need for contact lenses, and it's actually possible to replace the lens in the eye as well, okay, which I find crazy to attach that in to the suspensory ligaments and the ciliary muscles there, but it is possible to do. Okay, I hope you found that useful. Thank you.